If you have used deep learning model using Python, most of you might have heard or used either one of these two, PyTorch or TensorFlow, or also known as deep learning frameworks. So what's deep learning frameworks? Deep learning frameworks helps us make deep learning models. If you see what NVIDIA says about deep learning frameworks, it mentions that it offers building blocks for deep neural networks through a high-level programming interface, which is Python in case of PyTorch, and it relies on GPU-accelerated libraries to deliver high-performance, multi-GPU accelerated training. So, deep learning frameworks helps users use GPU computations by using GPU-accelerated libraries like cuda, cuBLAS, and cuDNN, which I'll explain it to you later. And it also helps making deep learning models by modularizing operations, like abstracting front and back propagation through modularization. Okay, but what does it mean to modularize its operations and why does it do that? And also, what does it mean when you say it supports GPU programming? Well, these two features are a whole different topic and needs to be separated. So for you to understand the basic concept of a whole framework, I want you to show you layers of the abstraction that I thought of when planning this project. Abstraction is really important when it comes to programming, especially when you make a deep learning framework, because one of the most important tasks we have to do is by abstracting repetitive and complex tasks in deep learning operations. We're abstracting two parts. The first part is about abstracting the core operations into functions using GPU and CPU programming. I'll first explain this by showing you an example of optimized operations. There are several libraries that offers optimized operation for Python, and NumPy is one of the Python library that enables numerical computing with Python. Python itself is really slow, but by using NumPy you can boost up computation by optimized algorithms. For example, when you try to do heavy, repetitive, and complex computations like matrix multiplication, you want it to be fast. So NumPy implements its operations in C and C++ and wraps up its operation into Python function, which is way more faster than naive Python. It also uses optimized algorithms. Maybe it could be Winograd, which optimizes by reducing multiplication, or maybe vector instruction implemented in SIMD architecture. But I'm not really sure what kind of algorithm they use. But the thing is, by optimizing and wrapping the operation into Python function, we can take the speed of optimized C code while maintaining the productivity that Python provides us. You can check the insane amount of time consumption that NumPy reduces compared to naive Python as the size of matrix gets bigger. PyTorch steps even further to optimize operations. The difference between NumPy is that it is more faster, since its functions use cuda, which uses GPU, to compute parallel computation really fast. Let's compare NumPy code that outperforms naive code with PyTorch, which is optimized by cuda. Torch code seems similar to NumPy since both libraries use matmul functions, but the mechanism running inside is different, since one is C and other one is cuda code. So when you compare the time consumption, even though NumPy functions are optimized, the time comparison between using CPU, which is NumPy, and GPU, which is PyTorch, is dramatic. This is an example of CUDA code that computes matrix multiplication using the method called tiled matrix multiplication. PyTorch use CUDA programming in their code for users to seamlessly communicate data between CPU and GPU, and let users focus on more important things like model architecture. But since we are making a deep learning framework, we have to implement these code by ourselves.
Yay.
There are also some implemented functions from NVIDIA libraries, like cuBLAS and cuDNN, that are optimized at hardware level to boost up deep learning core functions like filter to call. I also tried to use some of it. Don't feel too overwhelmed about it. I'll not specifically explain it to you right now, but make another video about it. For now, just know that we have to know this to make a framework. I started off this project by trying to implement a fused transformer function using cuda, using a method called flash attention from the paper of Tri Dao, which is pretty amazing when you find out the optimization you can do using same hardware. But this ended up being a whole deep learning framework for my school project. Anyway, this requires a lot of background knowledge, and this is for another long video that I'm gonna make. We're just going through the structure of abstraction, so again, try not to get overwhelmed about it. I'll explain it to you in the future video. After making a core functions that are optimized by GPU, we have to make an operation module that helps model to propagate front and back automatically. Deep learning models can have really complicated structure, and deep learning framework should support users to easily make deep learning models. In order to do this, I had to make a graph to track all the operations and connections between them. When I first tried to make a deep learning framework by myself, I had a lot of problems. I had to solve models like RNN that have a recursive structure that goes on and on. I also had to solve multiple endpoint problems that makes hard for model to know which one to differentiate. When there were multiple graphs in a model, I shouldn't backpropagate the graph that was not connected, so I had to solve all these problems. The first thing I've tried to make was an operation graph. When all the process is recorded into operation graph, it is possible to track front and back propagation. So how can I make an operation graph? I first stacked all the operations by making an operation class. I used C++ to implement this operation graph to use object-oriented programming. What I'm going to do is make a multiplication class that has forward method and backward method in it. Just in case, method is a function. When I call a forward method in multiplication class, I do original computation that needs to be done, multiplication. When I call backward method, I calculate the derivative of the values. This is the virtual class of all the operation classes. I'll explain it to you specifically in another video. After making an operation class, I made a model class to bind the operations into one function. Now I stack the operation in an array, and it just worked fine. I can't believe that this was it, so I tried in a repetitive graph, like RNN. But even with the recursive operations, by just using an operation array, I could easily do a forward and backward propagation properly without having a loop. I tried in a different example, another graph which is shaped like RNN, but this also doesn't make a loop in operation graph since there is an end in an operation array. But let's look at this graph. There are three ends in this graph, G, H, and E. If it tries to differentiate tensor G to all, it should not backpropagate operation 5 since tensor result G is not made from operation 5. The graph should not connect. Also, operation 3 should not be connected as well since it is in a different graph. But if we just stack the operations and execute in order, just like we did in RNN, it will call all the backward functions in order, which is wrong. So I have to solve this problem. So what we should do is we should track the tensors and filter what the graph has to differentiate. I'll show you an algorithm that do this in order. When it stacks the operations in an array, this should also store the information of connected upstream and downstream tensors. Upstream tensor means the return value of an operation, and downstream tensor means the input tensor of the operation. First, I had to make a list deriv tensor. We store the tensor that we are going to differentiate. We first call backward function that has an upstream gradient in the deriv tensor list. OP6 has G as an upstream gradient, so we should call backward function of OP6. After calling the operation, we put downstream gradient of an operation we called to the derived tensor list. Now, we go on to the next operation. OP5 has h as an upstream gradient, but h is not included in derived tensor list. We pass this operation and go to OP4. F is in derived tensor list, so we call backward function of OP4 and add WC in the list. And we go on to OP3. Upstream gradient of OP3, which is E, is not included in derived tensor, so we go on. And this goes on until we reach operation 1. And it seems it's working great. Well, I made this algorithm by myself, so if you have any points that you want to tell me, just please leave it in the comments. So, this is the end of the introduction of Easy Tensor. So from now on, I'll make the video of my code that I wrote. By first explaining the core functions, including the explanation of CUDA programming, and after that I'll tell you more specifically about operation and model classes and its structures. These structures are also used in ONNX, which is an open source neural network exchange graph, and I'm also planning to implement that as well. So please keep in track of my channel, and thank you for watching.